Go ahead.
Hi, I'm Nathan Zavanelli with the Ieee Urt Research Group at Georgia Tech, and our research relates to electroencephalography devices for brain-computer interfaces. So, traditionally, electroencephalography devices, or otherwise known as EEG, for these sort of brain-computer interfaces, or BCI, have used a messy 1020 electrode setup in order to read signals. But we've determined that instead of trying to read all of these signals from the brain across a variety of channels, some of which are very invasive to the user, like under the eyes and on the forehead, why not look at something called steady-state visually evoked potentials, or SSVEP? And SSVEP arise from signals in the light processing regions of the brain, the visual cortex, located on the back of the neck. So we've determined that we can use a two-channel setup, using two channels here under a headband that hides them from being readily visible. Two channels with a reference, a ground, on a flexible elastometer device that's mounted on the back of the neck. And for this device, we've determined that it can survive for 11 days, as of now in trial, including in water conditions. The user can shower with this device. It is waterproof. And we've determined that the conventional signals, the EEG 10 channel, provides a lot of erroneous signals that are not related to the SSVEP. And that becomes a classification nightmare for the machine learning algorithm. Now, when we do a power spectral density transformation of our signals, we get a very tight band of signal relating only to what we're looking at. As you can see here on the frequency spectrum, the two bands are centered right at the region that we're targeting. For this is the 11.1 hertz signal. So with that, it's very easy to design a neural network that can classify this signal as one of 5 different commands. The eyes closed command corresponds to a stop condition. That means that the device should stop. 11.1 hertz corresponds to moving forwards, and then we also have signals at 12.5 hertz, 15.2 hertz, and 16.7 hertz for left, right, and backwards respectively. So the way that we drive the brain-computer interface using this device is the user will look at one of a variety of lights, and based off of the window length that we choose, the device will read the signal for, let's say we choose 1 second. The device will then read the signal for 1 second, and after that amount of time, it'll classify the signal as one of 5 different types. Based off that classification, it will broadcast, at this point, the device is broadcasting to an application. It's broadcasting to an Android device or an iPhone device, and that iPhone or Android device will make the classification. So the device will say, okay, the user is looking at 11.1 hertz based off of the machine learning algorithm that we've designed. It'll then provide this classification to the device, in this case a wheelchair. So the user will look at the light for 1 second, after which the device will, the app will register, okay, this is a SSVEP signal corresponding to a move forward command. That will then be sent to the device, which will power the device, providing the command. The user will receive the feedback because the device will start moving, and then can initiate another command sequence after that. And what's really exciting about our research is that because we have such a tight band in the frequency domain for our signals, we're able to achieve accuracy of upwards of 94% for a 1.5 second channel versus conventional neural networks, conventional 1020 setup with accuracy below 80%. And in addition to that, our device is low obstruction to the user. It doesn't require messy gel electrodes, we use dry electrodes. And also, it is totally wireless and can be worn for upwards of 11 days in duration. Cool. Do you have any questions?
Thank you.